Alright, so this video is going to walk you through part 2 on the Google Doc for week 1. Before we jump into that, there's one thing I forgot to talk about last class, which might have confused you, but hopefully I can clear it up, which is just some notation stuff. So you might have noticed I was using an X with a little line over it. You might have been like, what is she talking about? So depending on whether we're talking about a parameter versus a statistic, we have different notation. For a parameter, we write the mean using the fancy M. For a statistic, that's where we use X bar. For proportions, if it's a parameter, we just use a regular P. If it's a statistic, we use a P with a hat on it. We call this P hat. And then last thing, for standard deviation, if it's for the whole population, for the parameter, we use that little that symbol that we've been using. If it's for a statistic, we just use a lowercase s. So you'll be seeing that stuff throughout this unit. Sorry I didn't mention that in the first video, but late's better than never. All right, so finding the real average for the chapter 6 test or the chapter 4 test. Should be F4. Okay, doesn't really matter too much. In part 1, we just looked at a very small class of 4 students as our whole population. In reality, there were many students, 31 of them, who took the test. Everyone's scores are listed below. I want you to take a random sample of 4 students. So how you do this is up to you. You can close your eyes and point. You can you can do like an interval. I forget what that's called because that was like units ago, where you like count off by like 6s or whatever to get your sample of 4. However you want to do a random sample of 4 students, I want you to do that. You're going to record their scores. So let's say, all right, I'm just going to pick a random number. I'm going to pick the number 8, and then I'm going to count off by 5s. Okay, so let's see, 1, 2, 3, 4, 5, 6, 7. So there's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so this is just one example, but my scores that I got from my random sample, I'm just supposed to do 4 students, so I'll cross off my last one. 0, 2, 4, and 6. It's asking you for the mean. So let's see, when I add all those up, I get 12. When I divide that by 4, I get 3. So don't use that one, do your own. I want you to do this 4 times. So 4 times, you need to take a random sample of 4 students, write down their scores, and find the mean. Pause and then hit play when you're ready to go over the next problem. All right, so I did this 33 times. It was super fun. And I got the following results for the means. I want you to try to answer questions 2, 3, and 4. I think you'll be able to make some progress on those. When you're ready to go over them with me, let me know. Or not let me know. Hit play, because I'm not going to be there. Okay, hit play, and then you'll hear me explain it. All right, so going to go over question 2. Each dot, what it represents is a random sample of 4 students. Was it 4 students? Yes. And the mean test score calculated for that sample. All right, next question. What do you think the true chapter 6 or chapter 4 test average is? Looking at this, I don't know, 3-ish? We're just estimating what the true average here might be. Obviously, we could calculate it. We have all the data here, but we'll just estimate it based off of, maybe 3 is a little high. Maybe it's more like 2.75. You can come up with your own estimate on that. Okay, last one. A sampling distribution shows the means calculated from all the possible samples of size 4 from the population. Is this dot plot a sampling distribution? So the question here, I underlined the keyword here, is basically, are we looking at all possible samples? The answer is no. There is a huge number of possible samples here. This is just 33 samples. how many would there be? Let's see, I'm going to calculate this. 33 times 32 times 31 times 30. There are actually 982,020 actual samples. We did not calculate all of them. So the answer is no. I should say that first. So in the graph, you're seeing 33 of them. There's like way more than that in real life. Well, yeah, okay. So last question. We took a random sample of 4 test scores at Washburn and got a mean of 2. Is this convincing evidence that Washburn students did worse than students at our school? Or is it possible that they would have the same average? So let's take a look at our dot plot here. They got a mean of 2. So I'm going to show you where that would look. That would be right here. And we're looking for anything that would be a mean of 2 or less. So we need to figure out, is that rare? Based off of our samples that we took, how rare is it to get a mean of 2 or lower? And I can calculate that. Let's see, 1, 2, 3, 4, 5. 5 times we got a sample with a mean of 5 or less. And I did this out of 33. So let's see, 5 out of 33 is 15%. So because that is higher than 5%, let's go ahead and put this in words. From our samples, we got a mean score of 2 or less, 5 out of 33, which is 15% times. 5% is our cutoff for both things being surprising and also convincing evidence. We're going to get more into that idea next unit, I think, coming up soon. So because that number is relatively large, and I know 15%, we might look at that number and think it's small, but like it's definitely bigger than 5%. So we're going to say it's relatively large. We don't have convincing evidence that Washburn's mean would be lower. And I know that idea is a little weird. We've sort of approached that concept a few times and it's always a little bit confusing, but we will definitely see it a lot more and it'll hopefully get more comfortable. Okay, so we're going to go through some notes and I think this might actually help. We'll see. Okay, so if we're going to evaluate a claim, there's a few steps to it. We're going to assume the claim is true. We're going to create a simulated sampling distribution. And then based off of that, we're going to find the percent chance of getting the observed result. All right, that might be a bunch of nonsense to you. I'll try to clear it up a little bit. All right, so assuming the claim is true, we are going to create a sampling distribution. So I'm just going to make up a dot plot. It's not even going to have like labels on it. That's okay. Okay, there's my fake sampling distribution. So whatever our observed result is, we can draw as a line. In the example we just did, it was Washburn's mean. In this case, it's a greater than claim, so we're going to be looking at what's the chance of getting greater than an observed result. And whether it's greater than, like in this case, or less than, like in this case, just depends on the problem. So if the observed result or something more extreme, and I'll explain what that means in just a sec as soon as I write down those words. We're never just looking at like, okay, what's the chance of literally getting exactly this value? It's always like that value or something even more extreme. So if that observed result, if it happens less than 5% of the time, we have convincing evidence against the claim. Because it happens so rarely. If it happens greater than or equal to 5% of the time, we do not have convincing evidence because it happens relatively frequently. Okay, I know that might be a little weird, so take a moment, look it over. The check for understanding is going to dive into this a lot more, so I want you to give it a try. Same as with part 1. If you get stuck, that's totally fine. If you have mistakes, that's totally fine. Once we go over it, it'll hopefully clear it up, but I want to make sure you're actually trying it first. So go ahead, pause, give the check for understanding a shot, and then we'll go over it. Okay, so looking at this check for understanding, there's sort of a lot going on here. Pennies made prior to 1982 were 95% copper. Because of their copper content, the pennies are worth about $0.023 each. Pennies made after 1982 are only 2.5% copper. Jenna reads online that 13.2% of pennies in circulation are pre-1982 copper pennies. She has a large container of pennies at home. She selects a random sample of 50 pennies from the container and finds that 11 are pre-1982 copper pennies. Does this provide convincing evidence that the proportion of pennies in her container that are pre-1982 copper pennies is greater than 0.132? So here we're working on evaluating a claim. The claim that we're evaluating is this, that 13.2% of pennies are pre-1982 pennies. Okay, so the population is all pennies in the container. Her sample was the 50 pennies that she chose. All right, so our parameter, and we're going to just assume this is true. Notice I'm using a lowercase p with no hat, is 0.132. Our statistic, which is p with a hat, and that's what she actually found. She found that 11 out of her 50 were the older pennies. So 11 out of 50 is 0.22. Okay, so question 2. Does she have some evidence that more than 13.2% of her pennies are older pennies? Yeah, sure. Her sample was much larger than 13.2. Her statistic, 22%, was higher than 13.2. All right, so 2 explanations. We're just kind of thinking like, why might this happen? So for one of them, we could say that the percent in the container is 13.2%, and she got her result just through luck. The other possibility would be that the percent in the container is really greater than 13.2. So it's like either it just happened through chance that her sample just happened to be bigger, or maybe the percent in her container of older pennies is actually larger than 13.2%. All right, question 4. We use technology to simulate selecting 100 simple random samples of size n equals 50 from a population in which actually 13.2% are pre-1982 copper pennies. So here is where we're doing that first step. We're assuming the claim is true. So we're setting up a simulation based on the idea that the claim is actually true, that there are 13.2% older pennies in her sample, or in her population. Okay, the dot plot shows p hat is the sample proportion of copper pennies for each of the 100 samples. All right, so if you were stuck so far, I want you to try again. So pause, see if you can make a little bit more progress here. When you're ready, you can continue and we'll walk through it together. Okay, so this is telling us for question 4, there is one dot at 0.22, aka 22% right there. What does this dot tell us? It tells us that one of the random samples of 50 pennies had 22% copper pennies. Copper or old pennies, pre-1982. All right, question 5. Assuming that 13.2% of pennies in circulation are pre-1982 copper pennies, is it surprising, is Jenna's result surprising? Is it surprising to get a sample of 50 pennies for which p hat is 11 out of 50, which is 22%? Justify your answer. Okay, so for this, I'm going to go find her result on the graph. So she had gotten 22%. I am interested in 22% or higher. So I always like to draw the line and the arrow because that's going to show me which side of the graph that I'm looking at. So based off of that, I can see that 4 of my samples had a result that was 22 or greater, 22% or greater. And let's see, there were 100 samples altogether. So 4 out of 100 is not 2%, 4%. That's literally what a percent is out of 100. Okay, moving on. So this is going to be surprising. It's less than 5%. So I'm going to say yes. Only 4 out of 100 samples had 22% or higher old pennies. Which is less than 5%. All right, so question 6 is related. Based on your previous answers, is there convincing evidence that more than 13.2% of pennies in Jenna's container are pre-1982 copper pennies? Explain your reasoning. Yes, we do have convincing evidence. Assuming the container had 13.2% old pennies, copper pennies, it is unlikely to get a result of 22% or higher. I'm running out of space here. Sorry. Yikes. Okay. That was a very unusual result if the claim was true. So that tells us that we actually have convincing evidence that the claim is not true. Okay, that's it for part 2. Go ahead and move on to part 3 when you're ready.